Okay, there we go. Today I'm going to talk about locally private hypothesis selection. It's a joint work with Ali Reza and Shahab. And before starting with the hypothesis selection problem, let me briefly review the LDP model. Unlike the central model here, each user, the randomization or privatization is done at the user side and released there. And what kind of randomization we are talking about? We can call it the epsilon local randomizer. One example, which is very useful, is the randomized response. Let's say you have a user's data that is a bit 0 or 1. So with some probability, you just output the correct bit. With some probability, you flip it, and this randomization helps to preserve privacy. So as the designer of an LDP algorithm, you get to choose what kind of local randomizer each user uses. So in this example, every user is using the same local randomizer. So let's say we have a statistical learning problem. We have IID samples that each users have. So different users have different data points. And each of them use the local randomizer that we tell them to use as the designer of the algorithm, and they don't have to be the same. So one important note here is that we have interactive and non-interactive algorithms for LDP, local differential privacy. And what is the difference? In the non-interactive setting, we choose the local randomizers a priori before seeing any information about the data. And the users run the local randomizers as we predefine. But we have also a sequential interactive setting that is run in multiple rounds. And in each round, we get to choose the local randomizers based on the outcomes of the previous round. And it's a stronger model, and we can do more things with this interaction, but we want to keep the number of interactions minimal. There is also the full interaction, which is not very relevant to this talk. So before defining the hypothesis selection problem, let me give you a gist of results in this area. Anyway, you want to choose from K hypotheses with whatever that means. So K is the important parameter here. Without privacy, the number of samples that you need to do this is logarithmic in the number of hypotheses. In the central differential privacy model, still it is logarithmic. However, in the local differential privacy model, it becomes linear. So there's a lower bound. So this is an interesting example of a problem that in LDP is much harder than central DP, exponentially harder. And okay, so what do we know about good algorithms for LDP? The best known algorithm prior to our work was this work by Gopi, Kamath, Kulkarni, Nikolov, and Wu Zhang, which was kind of the motivation of our work. So it's almost optimal. The number of samples that this one uses is slightly higher than K. There are some log factors. So we asked whether we can improve this, and we showed an optimal answer of K, a linear dependence on K. And the overall sample complexity is optimal when your epsilon is not very large. Okay, so aside from removing this log factor, there is also another corollary. We know that any non-interactive algorithm has to use at least klogk samples. So the fact that we could do it with K samples, our algorithm is also interactive. The fact that we could do it with K samples shows the power of interactivity and the separation here between interactive and non-interactive LDP. So in the rest of the talk, I'll first start with the background on hypothesis selection, and then at the end, a little bit about our algorithm and our new tool for analysis of such algorithms. Okay, so before starting with the hypothesis selection, let's start with hypothesis testing. Slightly different, but perhaps easier to describe. So you have, let's say, two distributions. You have some samples, and you want to figure out which distribution is generating the data. Here, you're assuming the data points are actually from distribution F1 or F2, exactly from one of these. And likelihood, non-privately likelihood ratio test is optimal for this problem. So there are two potential caveats for this formulation. First, we assume that the actual distribution is exactly F1 or F2. Maybe we want to relax it. Second, the number of samples that you need to distinguish between F1 and F2 depends on how close F1 and F2 are. In the hypothesis selection problem, we relax these. We say that, let's say the actual distribution H may not be F1 or F2. Instead, we only approximate the distribution H. We don't need to output H exactly. And what do I mean by approximation? We want to output a distribution that is close in total variation distance or L1 distance to the distribution H. So this is one formula that one of the formulas you see in this talk, because it's the definition of the problem. So it's good to take a closer look. You see a constant C here on the right side. It's called the approximation factor. You're saying that if your underlying distribution H is close to either F1 or F2, is very close to one of them, then you have to have a better accuracy at the end. You're required to have a better accuracy, C times that distance accuracy. Okay, so we want a constant approximation factor, and we want to choose between these two distributions. Okay, so what can we do for choosing from two distributions? There is a well-known standard Shefay test. So we divide the domain, we partition the domain into two sets. One set is all points where F1 is larger than F2. We call it set A. The second one is the rest of the space. So we have partitioned the space. Now we see the samples. We want to say whether it was from F1 or F2. We count how many data points are in set A, how many are not. Let's say in this example, 78% of the data points end up in A. Now F1 predicts 80% because F1 puts 80% of its probability mass on set A. F2 predicts 15% because it only puts 15% of the probability mass on A. So we choose F1 because it's closer to 78%. So that's the basic Shefay test, and it's robust and very nice. You can make it private and locally private very easily. Note that the only thing that we need from the data is how many data points are in A. So it's one kind of counting query or one question from the data. Counting question. So in order to make it LDP, you can simply run a randomizer and say if it was ask whether the data point is in A or not for each user, and they randomize and they give you the answer. What do we do for more than two hypotheses? We want to now choose between them. And again, a standard approach is to run some kind of tournament based on the primitive that we described in the previous slide. One kind of tournament is called a round robin. We play a game between every pair of hypotheses. So we have, if we have K hypotheses, we have roughly K squared comparisons or queries. And we return the hypothesis that has the highest number of wins in their games. So this one, there's a problem with it because it has too many comparisons, K squared, and later we'll see that it blows up the sample complexity. However, the good thing about it is that it's non-interactive. You get to choose the set A's before seeing the data, basically, your queries. Another algorithm is a single elimination knockout that we can think of, that you play this kind of tournament. Okay, the benefit is that now you have K plus K over 2, K over 4, So it's only k queries or comparisons. And here it becomes interactive because the next round depends on the winner who won the previous round. So we have log k rounds of interaction. There's a problem with this approach, which basically the approximation factor is not great, but it's a good conceptual algorithm. So let's take a look at all the algorithms within this area. So we talked about those that use k-squared, the round robin. So these are not great. And we also have the knockout that use log k interactions. Now we see the best known algorithm of Gopi et al. This one, the benefit is that it uses only log k rounds of interaction. And the sample complexity, again, is slightly worse than k. And we make it k. And one note is that all of the top algorithms have a log k factor in them, and it comes from a union bound because you are doing comparisons, and k or k squared comparison, they all have union bound, and we got rid of that. So how do we do that? We do a more careful analysis with the concept that we call critical queries. And the second one is that the improved algorithm. So maybe it's easier to see it in the knockout example to see how we avoid the union bound. So if you do it naively for a knockout, you will say that I have k comparisons and each of these may fail. So based on union bound, I get a k log k bound. However, if you do a more careful analysis, you will see that you have one, let's say F1 is the best hypothesis. You only care about F winning its game in every round. So in each round, there's one really important comparison, or what we call a critical query. You don't know which one it is, but it doesn't matter. In the analysis, still there's one. And this helps you to avoid the union bound. So we now want to design a new algorithm that uses a small number of critical queries and so that we improve the bound. So we kind of start with some kind of knockout in the beginning of the tournament because we want to go from k hypotheses to k slightly less than k, from k to k over log k hypotheses. And then from there, we do a combination of round robin and other things that maybe the details wouldn't matter. Another small thing that we do compared to previous work is that we boost the probability of success and we get logarithmic dependence on the failure probability. Okay, so let me conclude. We talked about LDP hypothesis selection, and we showed the optimal k number of samples, at least when epsilon was not so large, order of 1. And by this, we beat the lower bound for non-interactive algorithms. For this algorithm, we used only log k rounds of interaction, just like the previous work of Gopi et al. The question is that can we do it, an open question is that can we do it with less than log k rounds, even with 2 rounds, for example? We don't know. We only know that with 1 round, it's impossible. Another question is about non-interactive hypothesis selection. The best known non-interactive hypothesis selection uses k-squared comparisons or queries, but the lower bound is only k log k, so there is a big gap between the lower bound and the upper bound. So these remains as open questions in this problem. Thank you.
We have time for one question.
It feels like the algorithmic ideas you're presenting could be interpreted as improvements also to the non-private procedure in terms of not overall sample complexity necessarily, but like interactivity, number of like running times. Did you think about that? And do you know what what the new structures, like procedure tells you about the sort of non-private problem?
No, we didn't think much. Maybe at first we thought it wouldn't help because we get log k in the non-private, like only log k samples we need. And these are all k, log k, k, or k. So the difference would be big. But for non-private, in terms of samples, it didn't help at least because it's anyways log k only.
No, it was more.
But maybe computational, yeah, computational.
Yeah, like computation.
Yes, yes.
I mean, this appears in a paper of ours in 2023 to get like k over epsilon squared runtime. We have the same.
Yeah, so there's like a same idea from a paper in ICML of last year to get this like k over epsilon squared runtime using the same idea that you don't need a union bound and use all your samples.
Okay, I will ask you. Thank you.
Yeah, yeah.